Now I did. You guys forgot to remind me to start the recording. Okay. All right. So the Earth is moving apart. So here we go. Right. Chapter 3. What we're going to talk about is the air. These major areas. There's only 3 of them. These things we call marine provinces. So again, it's kind of like areas that we're going to talk about. Even within these marine provinces, it's kind of like where does one begin and the other one end. That kind of stuff. So this is dividing the world's oceans up into these 3 very broad kind of categories based on similar characteristics, though. So right back to where we were, right? There's the Mid-Atlantic Ridge, there's the Eastern Pacific Rise, and these things are spreading the Earth apart. So we've got these oceans. And of course, it's making up a good chunk of the world. Chapter 1, we said that maybe we ought to call Earth, what was it, Oceanus? Yeah? Because it really is a big, huge planet full of water. I mean, it just so happens, we are terrestrial organisms, so we think, well, it's about the land. But if you lived in the water, it'd be about the water. And really, when it comes right down to it, proportionally it is about the water. Water is extremely important. That's why, and I talk a little bit about this in Bio 1, quite a bit more in Bio 2. That's why water is so important to the formation of life on Earth, and that's why it's so exciting to astrobiologists when they find evidence of water, when they go, oh, look at this thing going around this distant star, based on some chemical signature they get, it looks like liquid water. Oh, wow, liquid water. Very cool, right? So that's why they always get so excited about that. All right, so, as long as human beings have been around, we've always wanted to know what was on the other side of the pond. People say, why did, I guess people don't say, but why did Columbus sail across the ocean? Why not? Let's see what's on the other side. Holy cow, if we never thought that way, we'd still be living in caves, afraid to go outside, right? That's not human nature. I remember as a kid, people would argue, why so much money in the space program just to go to the moon? Well, we got a lot of technology out of it, for one thing, and nobody would argue that. But you know what? Just to do it, it's kind of cool. It's why I got into science, watching that stuff on TV. I mean, come on. So when the world is made up of 75% ocean, you can imagine a lot of folks going, I wonder what's down there. Now, for a long time, people thought it was just flat and nothing, and that's, I was going to say, maybe easy to assume when you don't see it. So eventually, folks started thinking, we are trying to find out what's down there. So the British were very pioneer in this because, of course, the British were doing a lot of sailing around the world and colonizing and exploiting, gathering resources, however you want to call it, and it behooved them, it would be to their benefit to find out as much of the ocean as they possibly could, so they could understand currents and tides, and when there were signs of a coral reef to keep the ship away, when you should sail to this part of the world on this time of the year, watch out for this storm. Remember I told you early on about those folks they used to call pilots? And if you were a captain sailing your ship, especially around the world, you hired one of these know-it-all guys. And they knew, watch out for the reef north of that place over there where the birds fly south, And he'd always have this little book. And that was called his wheel book. And the wheel book was really valuable to a pilot because the wheel book had all his notes. All right, so 1872, that's a British ship, HMS. Was it Her Majesty's ship? I'm not sure. Anyway, so 1872... is the first official oceanographic expedition. Humans have been doing it since they've been making them stick maps that I showed you with Polynesia, right? But so here we are, 1872, and we can't see to the bottom of the ocean. We can't get to the bottom of the ocean successfully and come back, at least certainly back then. So the only way we're going to find out what the bottom of the ocean is like, and very geographically, is to figure out how deep it is. Okay, so we're going to take boats out, and of course back then people used to think the deepest part of the ocean was in the middle. Okay, well, like there's a big drain in the middle of the ocean, like a big pool drain, but we're going to find out it's not the case, obviously. So what they did is they lowered these things over the side with a weight on them, and if you've probably done it before. It's the same thing. How deep is the water on the end of the boat? You might stick an oar down there. You might drop something over, maybe the anchor, depending. But what you're doing is called sounding. And sounding is just basically getting the depth. And you're dropping this weight down, and you're seeing until it touches bottom. And that actual word fathom, which is been defined or standardized at 6 feet, just a little under 2 meters, was at one time. Oh, I can't show you in the here. My hands little. So if you're bringing a rope up from below, you would stretch the rope out, your arms with your spread of your arms, and then you pull the rope together, and you see what I'm doing? You're pulling the rope up. I don't know if you can see what I'm doing, but that was called a fathom, the width of your arms. Not everybody's arms are the same width, so they eventually went for a standard. But so that's what they were doing. They were going around measuring the fathoms of the bottom of the ocean, so the depth. And the reason why you could see one of the reasons why that'd be a good idea, because that's going to help you to prevent ships from running aground, right? Remember, it's that would be money and lives and materials lost. So it's important to know about this ocean, this bottom of the ocean, and how this ocean works, so we can develop these really neat underwater maps. And back then they were relatively crude because, oh, your book gives the number, and I was trying to remember it earlier. I've heard it a million times, but I think it's something like we know 80% of the sea floor. There you go. It's on the first page. 80% of the sea floor we don't have a detailed map of, a topographic map. Topographic is a height map, mountains and valleys and all that sort of stuff. 80% we don't have a detail. And I don't know the number, but there's probably a good percent that we have very little of any data about, right? We know more about the moon than the bottom of the ocean. But so we can take those soundings, but we'd have to take them. You can imagine what a pain in the rear end to go across the Pacific Ocean taking a sounding say if you even did it every 100 miles. Okay, so when things came along in the early 1900s, especially after World War I, and that's where sometimes need drives something. There was a need to detect submarines in World War I. And so scientists had already been working on this idea of using echoes to tell how far away something was, like say in radar. And if you put it in the water, you can do the same thing, right? So you send an echo ping. Here, let me play you an echo ping. You guys hear that? Yeah, now what's that doing in the water, that sound? Let me turn it off before we all go crazy. Stop! In other words, yeah, there you go. Moving the water particles, and that's sound, right? So sonar, which means sound navigation and ranging. But what I'm trying to get at, and I didn't word the question very well, is how does that tell someone listening to those pings how far away or how deep something is? So if I'm some dude on a ship up here at the top. Man, I am a horrible artist. That wouldn't even float. Okay, how does that do it? So I send out a sound. Ah, perfect. Yes, time, right? Because if I know how fast those ping, ping, ping things are traveling through the water, and then they bounce back, like when you yell against a wall or something. Come on. Anyway, so when the sound, it's not letting me drop. Anyway, so when it comes back, when it echoes back, now it does it. If you time that, right, you can figure out how far away something is. That's how radar works, and that's how sonar works in water. Same thing. Radar is radio detection and ranging, and sonar is sound navigation and ranging. Something very important, obviously, for submarines to navigate underwater. So when we use these echo soundings, and they get more and more sophisticated, and we'll talk in just a second about some of the really fancy stuff they got now, that does the same thing, Bradley. Absolutely. Yeah, that does the same. It's called dolphins, echolocation. This is, oh, hold on, let me turn off the sharing thing. This may, you know what? Just forget it. All right. So don't click on anything else, because apparently, I'll just close that. So Not that, just in case, honest. Anyway, so what we do is we have a ship on top of the ocean, right? And those things bounce off, and we use those, like echolocation I was talking about. Yeah, that's sonar, same thing. And we use those to get a profile of the ocean, right? So as the ship moves, let's say, from right to left across the top here, and it's going bing, bing, then it's bing. It takes long. I didn't mean to make it lower. It makes longer, right? It takes longer for the sound to come back. It's very simple. So then you can use that to give yourself a relatively decent, not horribly great map of the bottom of the ocean. Now, one of the things they found out that just blew people away was there was this false bottom. See that thing called the deep scattering layer? That's exactly. Yeah, that's right. That's how depth charges work. You would get a distance, you would get a depth to the sub, you would set the depth charge to that depth, and it would blow up. And the depth charge does not have to hit the sub to take it out. You're just basically underwater, like, you know, setting out a pulse, big sound wave, and that fractures the hull. So the reason why this is called the deep scattering layer, number one, it kind of puzzled everybody because it looks like a bottom when it's not, is it's scattering because it moved. Oh, what the heck is this? So at night, this would move up, and during the day, it would move down. So for many years, I mean, folks were like, what in the heck is doing that, right? What is this second ocean bottom that's this big to show up on sonar that's moving up and down in the water column at night? Well, come to find out, it was tiny little, in some cases, microscopic organisms, okay? Microscopic organisms would come up to the surface to feed at night, and then when the sun would come up and the predators would come out, they would go down to the deeper layer, you know, to hide during the day from these organisms. There were also other organisms that were actually doing the opposite. So they were rising during the day because they were photosynthesizing, and they were dropping at night. So you could actually have more than one of these deep scattering layers. So what was going on is these little critters, as they were moving up and down, there were so many of them. Each one of the little tiny critter, folks, there were so many of them. You know, just think about the amount of biomass there. It's moving up and down the water column. To show up on sonar like that, they give you like a false bottom. Now, speaking of submarines, from my Navy days, I remember that the deep scattering layer was also a good way for submarines to hide from sonar. Because as you can see in this picture, the sonar can penetrate through. But if you're at an angle, what happens sometimes with that sonar ping is it just bounces off of the deep scattering layer. It's kind of like throwing a rock, you know, into the water versus across the top of the water. Okay, now what soundings did in echo soundings, and again with the primitive nature that sonar started off with, they were able to start mapping the mid-Atlantic ridge. And that blew everybody away because, like I said, they thought the ocean was just this flat basin. But here was this massive mountain range. What did I say? 3,000 meters tall, some of these mountains were in some cases, with this huge valley in between, this huge rift valley. And that's back in 1925. Now, I didn't have a lot of detail, right? But you could see if we thought the bottom of the ocean was really nothing more than this big flat basin, and we're doing them pings across the ocean, all of a sudden we get this, you know, remember the rift valleys or the ridge is double, it's two mountains. That's why it's different than a regular mountain range. Regular mountain range is usually one, you know, core of mountains. But this is the rift valley because all the stuff pouring up in between. You can imagine 3,000 meters tall. Some dude's like, what the heck is that? Oh, yeah, that's what's, to me, is the ocean is so cool. Like all the stuff that's down there that we still don't know. Now today we can use really sophisticated digital echo sounders, things like C-beam, like you see in the picture with the ship up top, underneath the hull, and they go back and forth and back and forth and back and forth. And they basically do the same thing. Different frequency, more sophisticated sort of stuff. But what they're doing is they're basically reading the heights. And the darker the blue, the further away from the ship, or the deeper, and the more the red, the higher up, right? So they can look at the mountains that are underwater, the volcanoes, the ridges, and all that stuff. The thing with C-beam, though, it's kind of narrow. It maps the seafloor in 60 kilometers. That's about 37 miles wide. Okay, you know, that's a fair distance, but in the ocean, that's like, you know, that's like me trying to color in this whole page with my pen by just one line at a time. It's going to take a while. If you get Gloria, right? Gloria, I love these acronyms. Gloria is a geological long-range inclined acoustical. So acoustical means that what we're doing is using sound. Should be a parentheses there. We're using sound again, but the nice thing with Gloria, it's a side scan sonar. So you can actually read somewhere, you know, well, it's still about 60 kilometers across. But the nice thing about this too is Gloria also has a higher resolution rate in many cases. The only problem with Gloria though is the fact that you get this data gap because Gloria can't see right up underneath her. So like this volcano, which is over a mile off of Hawaii, a mile across, actually that's the data gap where Gloria can't see. Okay, Bradley, cool. All right. So, you know, and of course, all of these things, as technology has improved, and, you know, as we have a more sophisticated, higher resolution, we're getting more and more understanding. I look at that picture of the volcano down below. That looks, I mean, it looks like a photograph, right? And that's something we took from color enhanced by using these echo sounders. We're knowing a lot more, but the ocean's still a pretty big place. Satellites can really help, though, because satellites can take big, wide expanses of the ocean, and they can use that to do depth. Now, a satellite can't ping a signal from space all the way down to the bottom of the ocean. That's not going to happen. Well, what they can do is ping a signal from space to the surface of the ocean, the water surface. See, the outgoing radar pulses, they hit the top of the water. Now, believe it or not, when the water in the ocean flows over these different submarine things like mountains and canyons, it actually distorts the mountain a little bit. For example, your book says that a 6,500 high foot mountain, so a little over a mile, would actually distort the ocean, create a bulge about 7 feet. Now, in the middle of the ocean, you're probably not going to see that. Okay, but you know, if you're using a radar or a satellite that has something so incredibly sensitive that can actually detect it down to the inches, then 7 feet is going to be very obvious. So these bulges, or these anomalies is what they're called, these anomalies on the surface of the ocean actually are reflective of what's on the bottom of the ocean. Now, I know what you're thinking. What about in rough seas? Well, okay, what they do is they use something called a theoretical ocean surface. Now, off the top of my head, I don't exactly know how they calculate that, but they factor that in so that evens out. What they probably do is look at the average swell on Earth in that area of the ocean on a given day. So the average swell is 6 to 8. They might factor that in somehow, but regardless of how they do it, it's a correction factor. Okay. All right, isn't that neat? And of course, like I said, satellites, you can put bunches of them up there, go around and around and take a look at it. Let's take a look at Bradley's video there real quick, deeper parts of the ocean. Let's see how this works. A little deeper than that. Wow, that's incredible. Blue whales going down that deep. That's jeez. That's incredible. Very cool. Thank you, Brad. That's awesome. Very cool. I did. You're in the app share right now. Did it not play? Oh man. You're in. It says I am sharing. Did anybody else see that video? Didn't? Bradley, how about you? Or no? You saw me watching it. Hold on. This is all right. It said it was on. Let me try it again. I got that was kind of cool. I got to show that to you. Yeah. All right. Try it again. There we go. Now are you seeing it? Nice. Now y'all saw it, huh? Good, 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 good. Isn't that neat? You know what I thought? What I can't remember what they said exactly. Cameron went, or no, the deepest dive, the Bath Escape Trace went down just under 11,000 meters, if I remember right, at like 10,994 or something like that, and then the trench ends at like 11,003. Was that what it was? I was thinking, why didn't you go all the way to the bottom? I mean, if you went down that far, heck, I would have gone all the way to the bottom. Alrighty, folks, are you all back with me? I had to do that again. I gotta figure if that's me messing that up or that's a bug that every time I try to get out showing you guys a video, it dumps out my slides. Hello? All right, cool. Thank you, Chantel. Okay, so using satellites now, and even just those little anomalies, we get a lot better picture of the bottom of the Earth, like, or the bottom of the ocean. Like you've seen those two maps on the left, and they're in the book a little bit. Well, I can blow it up. The one on the top was made using bathymetry. Bathymetry is the study of depth, like I said at the beginning. That's what the Challenger was doing with the rope and the weight at the end. It's the same thing we're doing here with satellites or with ships. But if you do it by ship, you get, yeah, that's a decent picture. But look if you do it by satellite. Same area, but now you can, and this is, is that the Atlantic or is that the Rise? Yeah, is that the, thank you, Shinto. Brazilian Basin, okay. But you can still see, you can see the Mid-Atlantic Ridge much more distinctly on that. See it right there? That's the Mid-Atlantic Ridge. Now, remember these fracture zones or these transform faults? Basically, the reason why they occur is because, this area of rock might be moving just a little bit faster than this area. In other words, the speed along the Mid-Atlantic Ridge is all not exactly the same speed. So those rocks, as they solidify and stick together, they'll actually start to break. You can imagine if you had a big chunk of concrete like this, and you pushed it with different pressures. If you could do that, you would break it along a line like that. Okay, but you can see there's the ridge right there, right? So this is going over towards Europe and Africa, and that's going to North America. And then we've been able to use those to get this really neat map that you see on the right. And your book, the newer edition, actually has a better picture than this one. But the depths, again, are color correlated. So it really gives you a sense of, like look out here in the middle of the Pacific. It's the bottom, man. Way down there. And look out here at like the Atlantic. There's the bottom. And then look how much it rises up at the trench. And then this is the rise that we've been talking about. So now this is, you can see this is the big Pacific plate. I don't know if I'm tracing it exactly, which is, of course, where all the earthquakes happen, because from the rise, you got material moving that way and material moving this way. So when material moves this way, this is the Eurasian plate, is moving this way, right? They run into one another. They're what we call those convergent boundaries. And so they die below. One dies below the other one, the one with less density. So you make the trench, the Aleutian Trench, materials diving into that, and then the Marianas Trench was somewhere right off in here, right? So as we're making material, we got to be consuming material. All right. So back to this idea of how do we decide these provinces? Okay, we talk about the formation, the ocean, and how it's look at a very gross scale with the ridges and the rises. But now let's take a look at as we break those down. There are three major provinces in the ocean. We call them the continental margins, which is where you would fully expect them to be, right next to the continent. The middle of nowhere, that's the deep ocean basins. And then between those continental margins and those middles of nowhere is where the oceans are forming, the mid-oceanic ridges, like, for example, the mid-Atlantic. Remember, the mid-Atlantic ridge is not the only place that material is forming. The Eastern Pacific rise, not a ridge, but a rise, is also forming material. And it's symmetrical, for more or less symmetrical. The mid-oceanic ridge forming material. Why did it do that? Forming material moving along this line from left to right and right to left. I'm sorry, that way. And then the ocean basins, and of course, then the continent. So, this would all be part of a crustal plate, but this would be part of an oceanic plate, and then this would be part of a continental plate. Now, in the Atlantic, what's going to be happening, if this continental plate on the left is North America, South America, so point A, right? The mid-Atlantic or the mid-Atlantic ridge is pushing the material this way. So now if we could look at the other side of North America at the crust, we end up having, there we go. We end up having two what we call margins. We have an active margin and we have what's called a passive margin. Now that all has to do with plate tectonics again. It all has to do with how geologically active they are. So this is not the same picture that's in your book. I like this picture a little better, not that the one in your book is a bad one, but to me, I think this helps me understand a little better. Okay, continental margins are margins between continental crust and oceanic crust. Now, let's review. Oceanic crust is going to be denser than continental crust, so when those two things run into one another, what's going to happen is oceanic crust, the Nazca plate, say the one in the red, is going to dive down underneath the South American plate. So it's going to subduct. That's what dive down means. And of course, what's happening is the South American plate is moving from the east to the west because it's moving. The Atlantic Ocean is getting wider, and the Pacific is getting narrower. So when we talk about the active continental margin, in the case of South America, we're talking about the western a continental margin. We're talking about the coast that's on the Pacific side. That's the active one. That's where we get all this intense geological activity. The mountains of the Andes. See, that's what we call a continental arc. That's an area of volcanoes on land, an area, and of course volcanoes can be extinct or dormant, and whatever the case may be. But that's that's an arc of volcanoes, little pimples, right, that are forming because that Nazca plate and all the friction and the heat that's bubbling up. That's on the active side. On the active sides are always easier to tell. Think about the United States, right? The western coast of the United States is rockier. The cliffs in California, there's more cliffs, they're steeper. The shelf is a lot narrower out there. This continental shelf that we're going to talk about, steeper, things called continental slope. Everything is rougher, is the way I look at it. Everything is rougher on the West Coast. And that's because that's where all of this turmoil is happening. That Nazca plate is diving down below and it's bubbling up and it's causing these volcanoes. And when two plates mash together like that, there's also a wrinkling, remember? A wrinkling that occurs. So those mountains are wrinkling up, it's just chaos over there, even though it happened slow by our standards. It wasn't so slow in that Mount St. Helens video. And if you look at it from the side, you can see what I'm talking about. On the active side in the Pacific, you're going to have very little shelf, a very steep slope from the continent down to the bottom of the ocean, and that's where you're going to get your trenches. And there's not going to be this gradual lessening of the slope like you see over on the other side in the passive margin. See, the passive margin, you got a wider shelf. The slope is more gentle, and there's this thing called a continental rise. So on the active margin side, you're going to get this plates pushing together, and on the passive margin side, it's the trailing edge of the plate. You notice the Nazca plate, the one in the red, there's no subduction occurring over here. Pen would work. There we go. No subduction going on over there, right? No plate diving between the other one. All right. So passive sides are relatively inactive geologically, flat. We live on the passive side of the North American plate, okay? We live on the side that's the trailing. It's over in California where all the action is occurring. Now, passive margins, active margins and passive margins have all these features that I'm going to talk about here. But I want you to understand that the big difference between them is in the active margins, these features are much narrower. They're narrower, and in some cases, they don't exist. So that's why we call this a passive continental margin. But even active margins have a shelf and a shelf break and a slope. They don't have a rise. And, of course, everybody's got the abyssal plain when you get down to the bottom. All right, what is the continental shelf? The continental shelf is underwater. Don't get confused. This is not the edge of the beach right there. This is the edge of the beach right there. So the continental shelf is underwater. And you know, you walking out into the ocean, you know, it's shallow for a while. And average width is 40 miles or so, but it can extend way out there, especially on some of those passive margin areas that this is all trailing edge. That shelf can extend out to almost 1,000 miles. Now, just because it's a shelf and you can walk on it doesn't mean it stays walkable shallow forever. And especially in California, this is going to happen a lot more rapidly. But in you know, it can get out to depths of nearly 500 feet. So you couldn't walk to the edge of the shelf, right? And as I said, in California, like I said, that depth would come up on you a lot faster than that. Well, when you finally get to the edge of the shelf, and of course, when you're getting to the edge of the shelf and you're moving through the shelf break and the continental slope, what you're doing, folks, is you're hitting that boundary between oceanic crust and continental crust. Okay, so this is, you know, the asthenosphere is down below here, and these crustal plates are floating on them. All right, so the continental slope, this is where the deep ocean, the oceanic crust begins, and that can be a fairly decent slope. You know, especially, again, more so in California, but like about a 4% gradient, although it can get up to a 25% gradient. Think about it as percent. A 4% gradient would mean that the slope would drop 4 feet vertically for every 1 foot horizontally. So if you could imagine walking down a hill that is, no, it's the other way around. I'm sorry. You'd walk 4 feet horizontally and you drop 1 foot. Excuse me, reverse that around. No, it is rise over run. No, that's right. So you walk a foot. No, it's the other way around. Stupid math. Rise over run. Gradient is rise over run. Yeah, so it's your vertical that you walk. So if you had a 4 foot gradient, you've walked 1 foot this way and 4 feet this way. So that's your slope. But it can get to a 25-foot gradient. 25-foot gradient is like a cliff, right? Basically, it says if you take 1 step, you're going to drop 25 feet to the next place. So this slope can get pretty doggone steep. Again, more so in the active margins, but even in the passive margins, it can. And a lot of times, there's all kinds of stuff that's going on these slopes, like these submarine canyons. We'll talk about those in the next slide. But if you imagine a slope is just like any place where a river, you know, dumps into the ocean, those places in which those rivers or currents occur can actually erode this continental shelf in front of these massive canyons. I'll show that to you in just a second. Okay, the continental rise, we don't really find much of that on the active margins, but do on the passive margins, and just think of it as a place where the slope is coming down and then it's slowly beginning to level off into eventually the abyssal plain, right? Now, what happens a lot of times in these continental rises is you're right at the end of the slope, we can get these things called turbidity currents, and turbidity currents bring out these deposits. It's like a river, you know, flowing downhill and bringing all these rocks with it. So I'll show you that in the next picture too, and we'll talk about what a graded bedding is. And then we move off into the abyssal. Then we move off into a place that I'm thinking, man, it would be so awesome just to kind of have a laboratory down there, 4,000, 6,000 meters deep, flat. There is sedimentation in some places up to 1,000 meters or kilometers deep. Where would you think the sedimentation rates would be the highest in the oceans? What would you think if we were at the bottom of the ocean? Okay, shallower, a little more specific, shallow areas near what? Aha, see? You see that, what I'm showing you there of the Mississippi River, or the Mississippi River comes down. That blue line that you see is the shelf, all right? And then, of course, where it drops down would be the slope. And you can see that, the river has carved an erosive path through the shelf, and it's dumping out this what they call an alluvial fan. Alluvial fan is all this stuff washing down the river, spreading out and settling down as sediment across the Gulf of Mexico. Here's another alluvial fan. Look at the Indus fan. That's pouring out. Oh, what's the river on the west? The Ganges on the Indus. I would be very good at Jeopardy. I was always pretty good at geography, but I'm trying. What's the river on the west side of India? Anyway. Well, that's the Bengal River. All right. As the river pours out into the ocean, there, the same thing is happening. This huge, massive. I mean, the Indus fan is there's, you can get online and see reconstructions of it, but like people try to draw what it would look like. But I mean, it's incredible. It's just absolutely incredible. All right. I just tried to switch off of that and messed myself up again. So give me a second. I'll get right back. Let me find out about that. What's the red on the Indus fan? Oh yeah, it extends 1,100 miles south of the coast there. So that's how far that material spreads out. It just blows me away. The kind of the sizes and the magnitude of all this stuff. All right. Now sedimentation and as I said, they used to think that the entire ocean was nothing more than flat, and in some cases it actually is. I'm going to show you a picture in just a second. But in the middle of the ocean, there's not as much sedimentation because you're further away from the coast where a lot of it comes from. The abyssal plain, much more pronounced in the Atlantic, much wider in the Atlantic. Indian Ocean has a decent abyssal plain as far as size and magnitude. The Pacific, it's got a lot of stuff going on, folks. So there's a lot of deep areas, but there's not a lot of these huge, like Nebraska type areas underwater. There's a lot of volcanic activity, rumbling and bumblings, and volcanic pimples popping up, and trenches and things breaking. And it's, as I said, it's a pretty active place. All right. Let's jump on. Oh, yeah, let's go on to the fans again, those deep sea fans. So this is the Monterey Canyon off California, carved by the Monterey River, as well as a lot of other rivers, and based on the way the currents flow, you get this massive outflow of river and river. Remember, I was talking, well, that was my bio too. When rivers flow through things, they're like liquid sandpaper, because rivers are carrying rocks and little bits of grit. And so when it flows, when the river water flows down the Monterey Canyon, okay, it basically carves. You can see, you've seen it at the beach. It's what happened when the water flows back into the ocean, on the beach, right? But these canyons get big, like the Monterey one is, size of Grand Canyon. So this ain't no little canyon. And those are caused by turbidity currents. Turbidity is a measure of how cloudy, Okay, how cloudy the water is. Very muddy, cloudy water with lots of stuff floating in it, right? Stuff you probably would drink, has a very high turbidity. Clear water would have a very low turbidity. So things that are more turbid have more of that grit, right? And they can carve these canyons. This is thousands of years, but let me tell you what's kind of cool. No, well, maybe not so cool. But what's kind of neat about this is pretty close to shore, isn't it? Where do you think the big predators are going to be typically when it comes to finding prey? Are they going to be really up in the shallower waters where many times if they're not careful they might get too close into shore? Or is it a good place for a predator maybe to hang out in one of these near shore offshore canyons? Because humans or anybody else, any other critter, can oftentimes just be a little bit offshore, like off the Monterey Canyon, be in some very deep water. That's just kind of neat to think about, right? Out there floating around. I think about maybe you're floating around over the Monterey Canyon. You have to be fairly far offshore, but to think how deep it was down there. All right, so along come these big turbidity currents, and stuff is flowing down these canyons, and it dumps these big sea fans, like we've been talking about, the Indus one that I showed you and the one in the Gulf of Mexico. And dumping all that rock, and this is what we mean by graded bedding. We actually can see, the rocks are dropped based on their size. The small rocks drop first, then the middle-sized rocks, and then we get the larger rocks at the top. Oftentimes, we can actually look at the layers and judge how long sediment's being dumped in has been dumped in that canyon, which gives us an idea of how long the river's dumped in that region, or how long there's been these turbidity currents. So this picture of I guess I think this is a sound soundings using an echo sounder, and you can see what maybe the early folks may have thought, although they had no evidence to suggest. You can see that if you look at the ocean does have quite a bit of sediment. This is the sea floor. And then all of this are the mountains and the features underneath. So that's the nice thing about satellites too. Satellites can penetrate through this material, or not penetrate through material, but these bumps in the ocean floor. Now, a lot of times you do get some false readings because of this amount of this turbidity, but the abyssal plain is where you're going to have the biggest problem with this, because that's where the sedimentation sits. Our maps are going to be a little more accurate around the rift valleys, the rises, and near the coast, because this sedimentation is moved and it's scoured away. But out in the abyssal plain, where everything starts to settle down, then our maps might be a little less accurate because of the fact that even though we have all this actual crust, we have a ton of this sediment. See, so that's a problem out in the middle of the ocean. So in spite of the fact that even today our sounding suggests that that's flat, as technology improves, we'll be able to make things that actually see through that sediment. Now, there are things that can do that already. I'm not sure if they developed to the point of being able to see through a kilometer. Yeah, probably they have. All right. Let's talk about trenches and arcs. Trenches are where convergent boundaries come together. All right, so convergent crustal plates. In other words, plates that neither one is going to dive below the other one. Oftentimes, this is going to be an oceanic type plate, right? Two oceanic plates hit together, and usually about equal density. One may be a little less of density, but for the most part, they're going to kind of push each other, and you're going to get this V form that's going to shape. Now, in the cases where the oceanic plates, or it's an oceanic and continental plate, and the distance are different, or the densities are different, then you're going to get subduction, right? So you're going to get these trenches formed when they push together, and one subducts below the other one, and it forces it down. Plates can also kind of crumple together on these convergent boundaries, but either way, especially the ones where you get the subduction, you get the really, really, really deep ones, like 11,000 kilometers for the Marianas. So it's over 6 miles, like I was saying. It's relatively narrow. This is a deep, narrow trench, the Marianas. Around the Ring of Fire, because of the Pacific's activity, because that plate I was telling you about, you get a lot of these trenches around there, right? And you get a lot of convergent boundaries, so you get a lot of subduction. And wherever you get a lot of subduction, where you get a lot of trenches, you get a lot of volcanic activity. We even have some over here in the part of the world in the Puerto Rican Trench. The Puerto Rican Trench is relatively deep. It's what, 8 kilometers. So it's, you know, rivals some of the deeper ones over in the Pacific. But that's why there's so many trenches in the Pacific versus on the Atlantic, because that's where most of the subduction is happening. Page 94. Yeah, it's a little better picture. Thanks. All right, so you know, when we think about most of the world's volcanic activity, it is in that Pacific Ring of Fire, and the reason why it is because, again, these plates are pushing together, and that's where they're being absorbed back down into the bottom, being melted back into magma. All right. So as these trenches form, what happens on the okay? So there's the Peru-Chile Trench. If you look at Andes Mountains, so this is part of the South American plate, and this would be, I think, the Nazca plate. So there's 2 plates pushing together here. So in these areas in which you get this subduction occurring, you get trenches, like I said, a pretty deep one here. That's 8,000 meters. And on the part that's not subducting, so this plate is subducting, this plate is not subducting, you get these volcanic arcs. So as the plate dives down, that volcanic material bubbles up. It's less dense. It's like steam. It rises. So hot rock that's been you know, cooked, right, cooked down in the mantle, rises up, and it forms a material to serve as island or rock. The material is deposited on the surface until it builds up in the mountain. Now, there's what Mount St. Helens looks like today, by the way. That's the whole piece that got blown away in that video you saw. Look, you can still see that it's, I don't know if it's considered, it's not dormant. I'm sure it's not dormant. It's still considered an active volcano, I'm pretty sure. All right, I got to share again, so stick with me as I do this because I want to show you this video of an island. Oh, there's a neat shot of the deep scattering layer too. I forgot to show you this. This is a color enhanced computer generated, or not computer generated, but an actual color or computer color generated of actual data from a deep scatter. The green is the deep scattering layer. That. Did I somehow stop it? I might have. All right. I'm going to leave it on sharing. Are you guys seeing the whiteboard? Are you seeing volcanic arcs, island arcs? No, you're seeing the other stuff. So see, I can't do that. Okay, now are you seeing it? How about now? Hold on, folks, 1 second. I'm sorry. I'll get better at this, I promise. Hold on. Hello. Right there. Stop it. All right. Are we back? Thank you, Amy. So you can see the board now, though, or see the whiteboard now? Yeah, that's what I mean. I'm sorry. That's I didn't mean. I'm sorry. I kept saying whiteboard. Yeah. Okay, so as I said, that's why we find the trenches in the Pacific to the degree we do, because that's where most of that diving down below is occurring. So if we look at it from a side view over here near the Peru-Chile Trench, so on the other side, remember there's subduction occurring there as well. you can see that what happened is that subducting plate dives below, as the plate on the left dives below the continental plate on the right. It does a couple of things. It wrinkles up the continental crust forming mountains, right? So it does that to it. And it also, as it dives down, creates friction. The rock gets heated and bubbles up, if you will, because lighter rock is less dense, bubbles up into these Andes Mountains or into the Rocky Mountains, right? And some of them are volcanic, and some of them are volcanic for a while, and then they come back. There's extinct volcanoes, dormant volcanoes, and in the picture of Mount St. Helens is an active volcano. Now, if these volcanic arcs occur out over the ocean, all right, so we got two plates colliding over the ocean. It could be two oceanic plates, one a little more dense than the other. It could be a continental plate and the oceanic plate. Remember, the continental plates, a lot of it is still under the water, even though it's a continental plate, come into one another. But if that subduction occurs out over the ocean, then what we form are not mountains, but we form, islands in the ocean. We formed islands. That's how Japan was formed. Okay, that's a better example. That's how the Aleutian Islands in Alaska. So here's Alaska, and then the Aleutian Islands that extend out across like this, there's a trench right in front of it. And so those Aleutian Islands, Attu, Kodiak, what was the one? Adak. All right, my buddy was actually lived on for a while. But the land's diving down below, and the material's bubbling up from the ocean and forming these island arcs. Now, and again, an island arc is a volcano in the ocean. That's why there's so much. Mount Fuji is a volcano in Japan. Now, if this is happening between an area where a continental plate and an oceanic plate collide, the oceanic subducts, but the continental plate is over the proper land, right? Not just out over the shelf, if you will. Then we get the volcanoes on land. Then we get like what's in the Andes Mountains. That's what we get in the Rockies. Now, if you're in my Bio 2 class, you learn that one of the evidences that Darwin used in his theory of evolution by natural selection, that organisms have changed, was that how old the Earth was. And one of the pieces of evidence that was cited at that time was when Darwin stopped off in South America. He climbed up the Andes Mountain to see what was there, and he found marine fossils up there at the top of the mountain, at about 10,000 feet. Fossils of marine organisms. Now, the world didn't flood to that depth, but what happened is because this material was underwater at one time at the top of the Andes, and as the plate began pushing against it and wrinkling it up, it forced it to the surface. So we get a lot of evidence from many different walks of science. All scientists have to play together. They don't always play together nicely, but all scientists should have to. Okay. Oh, these are neat. These were discovered in the early, I was junior high, so 70, 71, somewhere around there, I believe they discovered these things. Okay, a hydrothermal vent is an underwater mini volcano. And what I mean by volcano is more functional. You can see in the picture of the upper left, what we have is the crust of the ocean, down at the bottom of the ocean, is not completely intact. There are cracks in it, right? The rock, when it cools and is moved around and pressured and pushed and all this kind of stuff, it develops fissures or cracks. Excuse me. So cold seawater, cooler seawater, will actually seep down through these cracks and become heated by a magma chamber, a lump of really superheated rock, of liquefied rock from the magma, right? From the mantle, from that asthenosphere place down below. Now, what that's going to do is that's going to rise to the surface, and it's actually going to begin to spew out the top of the bottom of the ocean. We're at the bottom of the ocean here. See? In this picture down below. So that's the bottom of the ocean. And so what's happening is it creates something called, like I said, it creates something called like a mini volcano, a black smoker. Now they have black smokers, and then there are white smokers, and then there are what we call warm water vents. And all of these are based upon, the way they look. Black smokers are really hot, and have a lot of sulfides and rock material bubbling up. Here's a black smoker. Okay, white smokers aren't quite as hot. They actually have temperatures in some cases down around no less than about 90 degrees Fahrenheit. But this material is bubbling up to the surface, and it's happening along these geothermically active areas. Some of the first ones that were discovered were in the map in the lower right, were right off the west coast of South America, in the area I circled in the blue, right near the Galapagos. And these smokers, these little mini volcanoes, cannot be so many. They can be up to 60 meters, close to 200 feet high. And again, this is a formation of material underwater. Now, the same thing happens, and that's the video I apparently got rid of that I wanted to show you, on the surface of the ocean. So this is the surface of the ocean. On the bottom, if a volcano erupts enough and deposits more and more material, now that's not what's going to happen with these black smokers because of where they're located, that you eventually go on to YouTube and type in ocean island formation. It'll form an island up above the surface. And the water is hot, in some cases 600 degrees Fahrenheit, but it's not steam because of all the pressure. Remember, when you make hot water turn into steam, you basically are causing its density to decrease. But if you have the water pushing down on it, water can't get less dense. Now, I know I've just got a minute, but I got to say something about these ecosystems. Black smokers, from a geological point of view, are fascinating, don't get me wrong, but from a biological point of view, they are absolutely astounding. Here's why. We didn't know they existed for the longest time. We didn't know that there were organisms that could live in this superheated volcanic water, but there are. There are organisms that live there that live no place else on Earth. Now, I'm not saying that they only live around hydrothermal vents. There are certain species of organisms that only live around one hydrothermal vent in one spot in the ocean, because in some cases they're that far apart. So if you move to another hydrothermal vent a mile away, there may be a different species of organisms living there. That's how unique these ecosystems are. All right, and I'm going to finish with one last thing, and I talk about this more on Bio 2. One of the possible hypotheses as to biogenesis, or the way life began on Earth, may suggest that it may have occurred or may have begun around these hydrothermal vents. Because around these hydrothermal vents, there's enough organic material and energy to create very complex molecules. And in the end, that's all living things are. It's just complex molecules engaged in complex chemical reactions, right? So if you want to hear more about that, that's my Bio 2 class. But if not, then don't take my Bio 2 class. But anyway, I'm done for the day. Let me turn the recording off, and I'll post this